Welcome, everybody. Good morning, good afternoon, good evening, depending on where in the world you are zooming in from. We are very excited to have Roger Creel joining us from Columbia University, and he will be talking today about glacial isostatic adjustment reduces past and future subsea permafrost. Before we get started with today's seminar, just a few quick announcements. Going a little bit over today's format, we are currently going over the welcome and announcements, which will be followed by Roger's talk for about 30 minutes, following which we will have a moderated question and answer that today Rehmat will be hosting. And after that, we will have a tea talk or tea time with our seminar speaker, who is Roger. And this is highly encouraged for students and postdocs to attend to, in an informal setting, get to know the speaker more. And if there are any outstanding questions, you can ask Roger those then. Don't forget to send any of your questions, if you have them, via chat to the questions at PaleoPerks, who today is going to be Rehmat. And a little bit about housekeeping. So PaleoPerks values the participation of all folks interested in the paleosciences. Please remember to abide by our code of conduct, which is available on our website. And if you are joining in using this link, you have most likely gone through the code of conduct. You should be muted during the duration of the talk, but for some reason, if you find yourself to be unmuted, please mute yourself. Again, you can ask questions by chatting to the questions at PaleoPerks host, who today is going to be Rehmat, and she will also be doing the question and answers time at the end of the seminar today. And if you also have any questions, you can use the raise hand function and we will unmute you and you can directly ask Roger your question. If there are any technical issues during the seminar, please again, send them via chat to questions at PaleoPerks host. We also have captions built into Zoom, and you can press the CC button to show or hide them. And you'll also find momentarily 2 links popping up into the Zoom chat. One of them is nominating speakers. If you know any early career researchers, we would love to hear from them. And the second link is going to be to the weekly feedback form, which is completely anonymous, highly encouraged. So we better know who is attending the seminars series. With that, I'm very excited to introduce today's speaker, Roger Creel. He did his bachelor's in geology and English from Amherst College in the United States. Following that, he got a master's in geophysics at Columbia University in the United States, where he currently is a geophysics doctoral candidate working at Columbia University's climate school. With that, Roger, if you would like to take over the Zoom.
Absolutely. And thank you to the PaleoPerks hosts and organizers. I have never been in such a well-organized speaking situation. And it's a great credit to you all for keeping this going, because I think it's a service to the community. So thank you so much. So I'm going to go into full screen mode. Are we looking okay?
Yes.
Yeah. Okay, great. So thanks everyone for coming. I'm going to talk to you today about glacial isostatic adjustment and its effect on Arctic subsea permafrost thaw. And I first want to thank my co-authors, without whom this would not be possible. I think anybody who thinks that there are like single genius scientists is just wrong. Albert Einstein's wife, for instance. So it's been a team effort. So I think the place I want to start is to say, to acknowledge what you may be thinking, which is permafrost and sea level. What? And specifically subsea permafrost, what? So here's a map of the distribution of present day terrestrial and submarine permafrost. Terrestrial permafrost is in brown, submarine permafrost is in green. And big picture, what you see is that there's a lot of permafrost. The US is over on the left side of the map, Eurasia is on the right side of the map. And there's a lot of terrestrial permafrost, but there's also a substantial amount of permafrost that is underwater. And here the color bar in green is going from 0 meters in very light green to more than 700 meters at darkest. And so the question is, how does it get there? How do you get permafrost underwater? And how much is there? Because this is an estimate from 2020. But if you could see the uncertainty bars on this, that you would see that they're quite large. And how is this permafrost going to do in a changing climate? How it forms is a fascinating question. So imagine the world 20,000 years ago. Ice sheets are covering North America and much of Europe, and global mean sea level, so globally average sea level, is 120 meters, give or take, lower. So that means the entire Arctic continental shelf is exposed to the air. Well, in the Arctic, air is very cold. So that means the entire Arctic continental shelf is freezing, and cold is percolating down. As climate changes over the deglaciation, going from 20,000 years ago to 9,000 years ago, sea level starts to rise everywhere because the ice sheets are melting. And that means that the Arctic continental shelf starts flooding. And this flooding continues to today, where continental shelves are totally covered with water, and the permafrost that was exposed at last glacial maximum is now submerged. But there was a long period where that continental shelf was exposed, and during that period it froze quite deep, which means that today this is a schematic of what the Arctic continental shelf looks like if you slice through it. So here depth is going down on the y-axis, and any ground that is frozen is in blue. So you have this complex pattern of sedimentary deposits that are pancaked on the outer edge of the continental margin. Some of the continental margin is frozen, other parts of it are not. But the question of how much is frozen and what the characteristics of that frozen ground are like that's actually quite hard to know, because, well, it's under the Arctic Ocean, and it takes a lot of resources to get ships there that are large enough that they can drill through the upper layer of sediment to get into this frozen permafrost. And until recently, most of this area was covered by perennial sea ice. So why should we care about subsea permafrost? I argue that we should care about subsea permafrost because it holds a lot of material that could become greenhouse gases. So this is a quite busy diagram from a review paper a couple of years ago, showing on top left our best expert assessed judgment of what permafrost extent was in millions of kilometers at last glacial maximum on left and at present on right. And what I want you to focus on or notice is, one, how big the error bars are on our assessment of just how much permafrost there is, and at that how much subsea permafrost there was at last glacial maximum is not that much less much less well known than our current estimate. So there are still some experts think that there's not very much permafrost there at all. Some think that there's more than 2 million square kilometers of it. The same is true for organic matter stored in this subsea permafrost at last glacial maximum and present. Error bars are pretty much the same, and they're huge. The same is true for the amount of carbon that is being emitted from this subsea permafrost. We have 3 orders of magnitude, more than 3 orders of magnitude differences in how much we think there is. And the same is true for methane stocks. Much of the methane that is stored in this subsea permafrost is stored as methane hydrates. This is methane that is solid under very high pressure, low temperature, so that when you bring it out into the air, it actually spontaneously combusts. And so it's not so. That's one way of noting that a lot of the organic material and potential greenhouse gases that's stored in subsea permafrost are quite unstable, which means that as climate changes, it becomes more and more possible that greenhouse gas may no longer be preserved within permafrost and may start to be released to the atmosphere. So that brings us to the motivating question. We have sea level in the picture, we have subsea permafrost in the picture. And so what I'm going to focus on today is the effect that sea level, and specifically sea level change caused by glacial isostatic adjustment, what effect does that have on subsea permafrost distribution and state? And if you're saying, what the heck is glacial isostatic adjustment? Great question. I'm going to spend some time talking about that because that's jargon and you shouldn't expect to know what it is. If you take away anything from this talk, big picture, take away these points. 1, there is permafrost under the Arctic Ocean, and there's quite a lot of it. 2, ice sheet growth and decay over glacial cycles, and the effects associated with changing ice sheet mass and changing ice sheet gravity affect sea level, and that effect is different in different places. So sea level is not a bathtub. And 3, human actions now can substantially reduce future subsea permafrost loss. Okay, so let's talk about some methods for the research that I'm going to be showing you. So in order to model subsea permafrost, as I said, it's quite difficult to get observations of it. There are some, there's some drill cores, and there are ways to use seismic imaging to image definitely the top layer of subsea permafrost, and to some extent the bottom layer. But mostly the way we build our understanding of subsea permafrost is through physics-based modeling that we then compare to observations. So the model that I'm using is based off of a 1D heat diffusion model that is open source. It's called CryoGrid. This heat diffusion model includes sediment composition, includes salinity. It distinguishes between marine and land sediment, and it has as forcing globally distributed geothermal heat flux. So how much heat is coming through the earth and reaching the surface. And what this model produces is shown in this schematic. So here depth is going down, and time schematically is going from left to right. So on the top axis, as temperature falls, increases, falls, anytime temperature is low, on the bottom axis, this is what permafrost looks like, or what the temperature profile of permafrost would look like. Anytime temperature coming from the surface is low, that cold percolates down through the sediment and freezes into this bluer color. geothermal heat is always coming from below. So anytime land is exposed, you can expect that the land is going to freeze from the top down, and that temperature from the top down will counteract the perpetual temperature heat coming from below. But if you cover permafrost with ocean water is quite a bit warmer than Arctic air. So once you essentially insulate continental shelf with water, then the permafrost starts thawing from below. So that's on the permafrost side. On the sea level change side, there are a number of different processes that change sea level over different timescales. We have ice sheets and glaciers growing and shrinking. We have the hydrological cycle, how much water is on land. We have ocean circulation. If you've heard of El Nino, the El Nino Southern Oscillation, you may know that depending on how strong that pattern is, you get more or less water that's essentially blown across the Pacific. And that's a property solely of ocean circulation and atmosphere effects. It's not related to ice sheets. So the process that I'm going to be focusing on, and that is dominant over glacial cycles, so over thousands to say a couple 100,000 years, is called glacial isostatic adjustment. So in this GIF, what you see is that as an ice sheet shrinks, the solid Earth rebounds and mantle flows towards the place where the ice sheet used to be. Whereas as an ice sheet grows, it depresses the solid Earth, pushes mantle out away, so it squeezes rock out from underneath it, and that creates what they call a forebulge or a peripheral bulge around an ice sheet. New York, New Jersey, some of the West Coast, Denmark, all these places are at the edge of where ice sheets used to be and are on the peripheral bulge of the ice sheet, which means that now, in our modern day, for people living in the US or Europe, if you're living at the edge of where the ice sheet used to be, then you are subsiding because the rock that got squeezed out during the last glacial cycle to lift you up by tens of meters is now flowing back underneath where the ice sheet used to be, flowing back underneath Canada. Okay, so ice sheets have this deforming behavior. They deform the solid Earth. Ice sheets also have a gravitational field. And that means that as an ice sheet grows, it attracts water towards it. So here on the top diagram, water is getting gravitationally attracted to an ice sheet. And then when the ice sheet melts, that water flows away. So there is a gravitational fingerprint of ice sheet growth and decay. There's a third effect that I won't spend a ton of time on, but is pretty nifty. So I just want to seed this in your heads that anytime you put mass on Earth that is not at the poles, you change the rotational axis of the Earth. So grow an ice sheet in Greenland and the entire Earth tips over. Melt that ice sheet and the entire Earth tips back. If you put all these patterns together, you get what they call a fingerprint of sea level change. So this is the fingerprint of what sea level change looks like when the West Antarctic ice sheet collapses. So down on the bottom of the globe, if the West Antarctic ice sheet collapses, and this fingerprint is normalized, so what you're seeing is how much sea level would change if you melted 1 meter of ice from enough ice from West Antarctica to raise global mean sea level by 1 meter. So if you melt enough ice from West Antarctica to change global mean sea level by a meter, sea level actually falls around West Antarctica, but sea level rises by 1.5 times as much some places far away from West Antarctica. So we put all this together. We put the permafrost together with this sea level change caused by glacial isostatic adjustment, and we create a model of relative sea level change over the last 4 glacial cycles. So over the last 400,000 years or so, we model what relative sea level was everywhere, and we use that relative sea level to determine in the permafrost model which locations are flooded by ocean water, which locations are exposed to air. And then we push 1,000 years into the future for a range of ice sheet projections based on different climate change scenarios. So how much is the Greenland ice sheet going to melt in the next 1,000 years if humans put a lot of CO2 into the atmosphere versus not so much? And the same for Antarctica. So let's talk about some results. This is a map of how thick our modeled best estimate of how thick subsea permafrost is now. And we find that subsea permafrost is thickest in shallow areas of the Arctic continental margin. This makes sense. Shallow areas have been exposed to the atmosphere for the longest period of time over the last 400,000 years. And in deep areas, we find permafrost that is closer to 100 meters thick. Most permafrost is in areas where there have not been ice sheets. So a lot of the Arctic continental shelf in Russia, Siberia, but off the coast of Norway, down in the lower right of this image, there's no subsea permafrost because there have been ice sheets there for so long. And there are two, we've talked about two main drivers of what changes subsea permafrost over time. One of them is global mean sea level, and the other one is glacial isostatic adjustment. So I'm going to break out, show you the influence of those two effects on our model and how this model, how these influences have updated our assessment of subsea permafrost from previous work, which did not include glacial isostatic adjustment. So we find that global mean sea level and ice sheets have a substantial impact on permafrost thickness. So it turns out that that if you adopt a depending on what your global mean sea level history is, that will control what fraction of time much of the Arctic continental shelf is exposed. So in the global mean sea level history that we've adopted, we find that we model quite a bit more permafrost in deep parts of the continental margin and much less in shallow parts. Glacial isostatic adjustment has a smaller but still significant impact, and that impact is felt principally in areas near ice sheets, and I'll explain why in a second. But there's also an effect that happens farther away from ice sheets, where in places there we lose a little bit of permafrost, and in deep parts of the continental margin we gain small amounts of permafrost. So first, looking at the impact of global mean sea level. So the last best estimate of subsea permafrost used the model, the global mean sea level model that is traced out here in black. And the global mean sea level estimate that we use here, we're going from 400,000 years ago at left to 0 at right. And global mean sea level is going from 0 at the top to negative 125 meters. These different gray bands are corresponding to different marine isotope stages. Because the global mean sea level history that we're using is deeper at glacial maxima, so any these blue peaks, these blue troughs are showing where our global mean sea level history is deeper than the previous version. Because of that, we get more permafrost, subsea permafrost formation on the deep parts of the continental shelf, whereas our global mean sea level history is shallower, is higher for much of these periods, and that means that we get less permafrost. And that brings us to the impact of glacial isostatic adjustment, the second factor here. And to answer that, I want to show you the impact of gravity, ice sheet gravity, and ice sheet deformation. We talked about those two factors as both being important. So on the left, this is a map of the effect of glacial isostatic adjustment due to ice sheet gravity at last glacial maximum. And on the right is the effect of ice sheets deforming the solid Earth. So what this is showing you is that near to ice sheets, the ice sheets are outlined in black. Inside ice sheets, the extent of the ice sheet, so basically underneath an ice sheet, the gravitational effect of the ice sheet is drawing water towards it, just like we talked about. And then farther away from the ice sheet, sea level is falling because that water got drawn towards the ice sheet, so there's less water elsewhere. Whereas the deformation picture, the ice sheets are heavy, they're weighing down the ground underneath them, but then also they're weighing down the areas right around them. Think about if you sit on a memory foam mattress, you have this divot. And so that's the primary effect. And then there's also an effect related to the continental margins further away from ice sheets. Here's a map of, again, showing ice sheets at last glacial maximum, and the difference at these red, blue, and purple dots, the difference between global mean sea level and relative sea level. So global mean sea level is in black, and these different colors are showing these different locations. So at the top, we see that far away from the ice sheets, this red dot is very close to global mean sea level. But as you get closer to the ice sheets, like the purple dot, global mean sea level is quite a bit different from relative sea level. So if you're standing right next to the Barents Sea ice sheet, and stay there for 100,000 years, the relative sea level that you're seeing is quite a bit different. So I've been showing you time slices, but I think it's also instructive to look at the mean permafrost thickness that we are modeling through time. And so here time is again going from 0 at 400,000 years ago at left to 0 at right, and then we project 1,000 years into the future. And what you see is that as global mean sea level falls into a glacial, you get a lot of this light colored, this light green color is showing how thick mean permafrost is in the entire modeled region. And then as sea level rises, you get a snap, very fast increase in subsea permafrost because you flooded the continental margins. And then that permafrost slowly disintegrates through time. And that pattern happens every time global mean sea level falls and rises. In the future, blue is a low emissions scenario and purple is higher emissions. So with low emissions, permafrost slowly thaws, but as we add more CO2 into the atmosphere, we get this step change around 2300, and then all of a sudden, subsea permafrost starts melting very fast. And here's why. This is a figure showing benthic, so deep water temperatures from 1900 to 3000. This is modeled temperatures, a projection. And what happens around 2300 is, and even starting around 2150 in the future, is that as soon as we lose sea ice, Arctic sea ice, that taking the lid off the Arctic means that Arctic ocean bottom water temperatures pass a threshold where they're no longer less than 0 degrees Celsius. So they're no longer below freezing, which is it's possible for water to be below freezing so long as it's saline. But once Arctic bottom water increases temperature above 0, then the permafrost is thawing both from above and below. And that makes it thaw very fast. This is our projection with low emissions on top and high emissions on bottom, how much permafrost we lose by 2300 and then by 3000. And what I want you to focus on is the difference between low emissions at 3000 and high emissions at 3000, or even at 2300. There's a significant difference between losing all permafrost for subsea permafrost for much of the continental margin with high emissions versus not more than about 20% with low emissions. And I think it's important for future planning purposes to note that the present thickness of subsea permafrost is a quite good predictor of its future disappearance. So permafrost that is quite thin, so here thickness at 1850 is on the y-axis, will disappear much sooner. So time of disappearance is on the x-axis. Thin permafrost will disappear much sooner than thick permafrost. And this is true for both low emissions and high emissions. Low emissions is on the left and high emissions, low emissions, is in purple and high emissions is in blue. My last slide, I want to show you how future rates of subsea permafrost thaw projected will compare to rates of subsea permafrost thaw over the last 4 glacial cycles. So thinning rates here are on the y-axis, and time is on the x-axis. And so thinning rates over the last 4 glacial cycles in a low emissions scenario in the future in blue, we continue to thin at the same rate, but with high emissions, we increase rates of thinning by 8 times, starting at 2050, and then rates slow down but continue at 4 times historical and prehistoric rates for the next 700 years. So with that, I want to leave some takeaways here. 1, ice sheet history and global mean sea level significantly influences subsea permafrost thickness and distribution. 2, adding glacial isostatic adjustment thins present-day permafrost. present-day permafrost in all shallow continental shelf areas. And then in the future, under low emissions, we continue the pre-industrial thinning rate and less than 10% of permafrost area disappears, whereas under high emissions, thinning rates increase to 8 times faster than pre-industrial for the next 300 years, and then slow down to 4 times pre-industrial after that. And by 3000, we lose more than 60% of subsea permafrost by thickness and 50% by area. So with that, I want to thank you for your attention and open myself up for questions.
Awesome. Thank you so much for such a great talk. I definitely learned a lot about glacial isostatic adjustment, and your data were really cool. A quick reminder to the audience, you can send your questions in to the questions that PaleoPerks host directly. We handle these questions either with your name if you'd like it to be named, or anonymously as well. So we have a couple of questions in already. So I will pop each of these in the chat for you, Roger, so that you can read them and everyone can follow along. So the first one we have is from K. Sender Salwan. And Sender asks, how old is the organic matter and methane that is stored in permafrost? How and when is it accumulated, e.g. during a thawing stage or afterwards?
Ah, that's such a great question. Thank you for asking that. So my glib answer is you would have a banger paper if you could convincingly answer that question, because I think how old organic matter and methane is in permafrost is modelable, certainly, but really requires data. And the challenge with dating organic matter that old is that older than 45,000 years, you can't use radiocarbon. But other techniques that we might use, like optical stimulation luminescence dating, won't really apply. Well, potentially, actually, you could use optical stimulation luminescence. But basically, what you would need to answer that would be a lot of sediment cores from the Arctic continental shelf that you could date, get age models on. And we don't have those right now. I think the answer to how and when it is accumulated, also a great question. So imagine you have, during a glacial maximum, the continental shelf is exposed, so you're getting terrestrial permafrost formation, just like we have now, which means that during Arctic summers, there is biomass. It then gets frozen and stored in permafrost. So there's a substantial amount of terrestrial organic matter that's getting bound up into what then becomes subsea permafrost. There's also organic matter, marine organic matter, that gets deposited when the Arctic continental shelf is flooded. That's, of course, of a different type. It's a different type of organic matter, but you're still getting phytoplankton raining down, everything else that you get on modern continental shelves. And then that, when sea level retreats, as ice sheets grow, that organic matter would also be frozen. So it's a very cool layer cake pattern of marine organic material and terrestrial organic material, and exactly how much is in there is a hard question to answer.
Great, thank you so much. So we have another question for you, which is an anonymous one. So what do you think is the mechanism driving the increase in deep Arctic water in the future around 2100 CE?
Yeah, another wonderful question. So I can tell you the mechanism that we are modeling And I can tell you the reasons for that mechanism. It is in the future. So the problem with future projections is that we don't actually live in the future. But the mechanism, the hypothesized mechanism for what is going to happen to the Arctic around 2050, 2100, depending on the future, is that as sea ice extents continue to shrink, and at a certain point in the next couple of decades, we're probably going to no longer have perennial sea ice in the Arctic. So Arctic will start to be ice-free during parts of the summer. And then moving forward, depending on how humans behave, it could become more and more ice-free. Ice has a much higher albedo than water. Ice reflects a lot more solar energy than water. So just from that alone, once you have the Arctic no longer covered by a white parasol of sea ice, but once it's open water, that the Arctic Ocean starts to absorb a lot more heat. And I'm going to quickly reach the limits of my oceanographic understanding if I venture down this route, but I also think that there are significant changes in ocean circulation that kick in once you lose sea ice, because sea ice protects the Arctic Ocean essentially from storms, and decreases the fetch, decreases the distance over which wind can blow. So as soon as you have an open Arctic, you start to get a lot more storms, and you get a lot more wave action, and that I think also catalyzes more mixing and ventilation of the Arctic Ocean, which would then drive warm water from the surfaces down deeper. And on the continental shelf, deeper is not actually that deep. We're talking about 100 meters. So it's quite feasible to imagine that the Arctic Ocean is, the continental shelf bottom is going to start to be warmer than 0 degrees Celsius.
Thank you. We have another question in from Case Andrew Solomon again. So does organic matter and methane stored in permafrost get affected by diagenesis caused inherently by temperature fluctuations? If so, is diagenesis in polar regions different to other regions globally?
I think any paleo talk that doesn't get a question about diagenesis is missing out, because yeah, diagenesis is a big factor. So diagenesis being the effects that happen to typically stratigraphy after deposition. So in the rock world, we think of diagenesis as what happens to typically sedimentary rocks, but other rocks also after they're lithified, indurated, but not quite at metamorphic temperature grades. Here, diagenesis, I think, maybe you would think of as what happens to the permafrost after it's frozen, or what happens to the organic material after it's emplaced, maybe. And there's a huge debate. I think it's kind of it's delightful to witness, and I think it's good for the permafrost community to have this debate. I don't like people arguing with each other, but it's necessary. So the debate is how much of the organic material, as it gets respired, as it gets chewed up, and methane, how much of that organic material is going to make it out through the water column to the air as methane, as CO2, as greenhouse gas. And as I showed in one slide about expert assessment of, actually, maybe I can go back. if I'm still sharing. The experts, come on, a little bit further back. Experts really don't agree on this. So we're looking at carbon flux. So this is how much CO2 is getting, what is the CO2 flux out of subsea permafrost? And I'd have to check if this is to the atmosphere or not. I think it's to the atmosphere, but CO2, oh, and then methane into the water column versus methane into the atmosphere. And so, right, estimates are going from 0.001 megatons per year, so basically nothing, to almost a gigaton per year now. And a big question in that discussion is the role of diagenesis. I think your intuition, questioner, about temperature is a good one. So reactions happen faster typically at higher temperatures. So if you increase bottom water temperatures a few degrees, you would expect there would be faster respiration. And I think concerning diagenesis in polar regions versus other regions, diagenesis in ice is its own beast, because you have the phase changes of ice to water. There's also cool interactions between ice and sea and salt. So salt percolates down through the ice, and that can inhibit ice formation and change the ice properties. So yes, I think sedimentary diagenesis on continental shelves is different in polar regions, principally because of the ice. And I think we don't really understand. I feel pretty confident about saying not just I don't understand, but I think we don't understand much of what's happening diagenetically to organic material in permafrost underwater.
Nice. I also enjoy diagenesis questions at Paleo Talks.
I know.
Yep. So we have another question that's come in, which is an anonymous one. So, are you able to constrain the significance of seasonality in modulating variability in the permafrost using the model for the present? Using that, could you infer something about the importance of seasonality and its impact on subsea surface permafrost at the last glacial maximum?
Oh, wow. That's a wonderful question. I think seasonality is one of the factors that we're just, well, I may be myopic, but I think a lot of the paleo community hasn't paid enough attention to seasonality. And seasonality in proxies, I think, is certainly a huge factor for temperature, etc. How do we apply seasonality to permafrost variability in the present? So let me think about this. So in the present, if we're applying it specifically to subsea permafrost, the way you would see seasonality would be primarily in differences in bottom water temperature. And I don't know of anyone who has looked at that for permafrost in the modern environment on a pan-Arctic scale. I'm going to go search for papers on that, but currently in the model, we have been using annually constant bottom water temperatures. And I'm embarrassed to say that I don't have a great grasp on how much Arctic bottom water temperatures vary over seasons. I imagine it could be substantial, and I also imagine that there'll be an interesting liminal period between now, when sea ice covers most of the relevant parts of the Arctic for most of the year, and where you could expect that there wouldn't be a ton of seasonal temperature variation. And once we get into the winter sea ice, summer not sea ice, then you could see a lot more variability in temperature, bottom water temperature. And that probably would drive some interesting fluxes into and out of the system. I think there's some cool work being done on seasonality in coastal permafrost. So this is work by Julia Guimond and others, who's at Woods Hole, looking at when is seawater getting drawn into coastal permafrost, which times of the year, and when is freshwater flux pushing out into the continental shelf. And the interesting thing about subsea permafrost is that you can have freshwater flux from the coast that basically dives underneath the subsea permafrost and then outwells at the edge of the continental margin. I saw a talk at AGU on this past year. So I could imagine that once we get into this place where there's a lot of seasonal variability in in like benthic Arctic bottom water temperature, that might turn into a pump that could draw fresh water off the continent and out onto the continental margin. And that might have a substantial impact. I think at last glacial maximum, I would expect that there would be less seasonality, or it would be less important because the entire Arctic is frozen. Here's another interesting debate in the paleo world. If not at last glacial maximum, what were there times during the Quaternary when the entire Arctic was frozen solid, like the Arctic Ocean was frozen solid? I don't think we have resolution on that. I see papers battling about this, but whether or not the entire Arctic Ocean was frozen, definitely from the shore out past the edge of the continental margin, the shelf break, that was definitely frozen, probably ice shelves, and then you would get similar behavior to what we see in Antarctica right now, like whatever is happening underneath the ice shelves in Antarctica, or whatever happened. I mean, now the ice shelves are not doing great, but there would have been ice shelves on the Arctic at last glacial maximum, covering all of this. Well, the ice shelves would have been extending from the edge of the continental margin out into the ocean. So, and yeah, so actually, let me reframe that then. So what we're considering, the permafrost that we're considering right now, is not covered by water during last glacial maximum. And there would not, the subsea surface permafrost at last glacial maximum essentially wouldn't have existed, because last glacial maximum was one of the bigger glaciations in the Quaternary. So sea level would have been as low as it has been in quite some time, which means that there would essentially be no submarine permafrost, or very little at last glacial maximum. That was a long answer.
That's great. So we are at 5 to the hour. So I'm gonna end the Q&A and do a quick outro. So thank you everybody once again for joining us, and thank you very much to Roger for such a great talk with lots of really interesting science stories. So to the audience, please remember to fill out our weekly feedback form, and we'll post the link in the chat very, very shortly. so that we can find out a bit more about who attended today's seminar. And join us next week on May 23rd at the same time, where we'll be joined by Carlos Marques from Universidad Competente de Madrid in Spain. And Carlos's talk is entitled The Quaternary Paleobotany of Madeira and the Azores Volcanic Archipelagos, Portugal, Insights into the Past Diversity, Ecology, Biogeography, and Evolution. So I hope to see you next week.